So this is Mr. Martin. These are the video notes for math analysis, section 11.4. We're going to be looking at limits at infinity. So in calculus, we basically have two problems. We're finding tangent lines, and then we're going to be finding areas of a region. So in the last section, we learned how limits could be used to solve the tangent line problem. We used the difference quotient. Now we're going to look at the limit at infinity. They can be used to solve the area problem. So to get an idea of what is meant by the limit of infinity, let's look at the following function. We have f of x is equal to x plus 1 over 3x. And we know that there's going to be a horizontal asymptote at y equals 1/3. And then if we use limit notation, the limit as x approaches negative infinity of f of x is going to be 1/3. And then the limit as x approaches infinity, positive infinity, is also going to be 1/3. So if we take a look at the graph here, what these limits mean that the value of f of x gets arbitrarily close to 1/3 as x decreases or increases. So here's the graph of this function, and then we've got our horizontal asymptote right about here at 1/3. And then you can see as we approach infinity as we approach negative infinity, we're getting really close to 1/3. Here's our 1/3 right here. And as we approach positive infinity, we're also getting close to that same asymptote 1/3. So for our limits at infinity, if r is a positive real number, then the limit as x approaches infinity of f of x is going to be 1 over x to the r. Okay, so keep in mind as x gets larger, as this denominator gets larger, the fraction is going to get smaller. That's why this approaches 0. And if x to the r is defined when x is less than 0, then the limit as x approaches negative infinity of f of x is also going to be 1 over x to the r, which is also 0. So what we want to do is we want to try and change our functions using our properties of limits into forms of fractions that we can find the limits of. So let's take a look at this first example. And I'm going to rewrite this using my limit properties. So I've got the limit as x approaches infinity of 5 plus 3/2 times the limit as x approaches infinity of 1 over x cubed. So now we have the limit as x approaches infinity of 5 is just going to be 5. And then we're going to have plus 3/2, and the limit as x approaches infinity of 1 over x cubed is going to be 0. So this is times 0. So then our final limit is 5. Alright, so important note here, when evaluating limits at infinity for more complicated rational functions, you will want to divide each term in the numerator and denominator by the highest powered term in the denominator. Alright, so just a little technique here for solving these. So let's take a look at example A. So our highest powered term in the denominator is x squared. So what we want to do is divide every term in the limit by x squared. So we're going to have the limit as x approaches infinity. And in the numerator, we're going to have negative 2 over x, because when I divide by x squared, one of the x's is going to cancel out, plus 3 over x squared, all over, now divide each term in the denominator by x squared, so 3x squared divided by x squared is 3, and then plus 1 over x squared. So then we have each of our terms in terms of a fraction, so we can calculate our limit. We could divide it up the way we did it in the first example, but I'm not going to in this case. So now the limit as x approaches infinity of negative 2 over x, as x gets very large, this is going to approach 0. Same thing for the second one. 3 over x squared is going to approach 0. And then the limit as x approaches infinity of 3 is going to be 3. And then again over here, I have plus 0 as x approaches infinity. This is going to get very, very small. And we can see that this limit approaches 0. So example B, if you want to go ahead and pause the video and give it a try on your own, feel free. Otherwise, I'm going to work through it. So again, I'm going to divide everything by x squared. So we have a very similar problem. We have the limit as x approaches infinity. So I'm going to divide this term by x squared. So I get negative 2, divide the 3. So I have 3 over x squared. Moving on to the denominator, 3x squared divided by x squared is 3, plus 1 over x squared. And then, so this limit is going to be negative 2 plus 0 over 3 plus another 0. So now this limit is negative 2/3. Alright, and as usual, if you have questions, if you're watching in class, go ahead and pause the video and track me down and ask your question. Otherwise, if you're outside of class, write your question down in the margin so you can ask me next time you see me. So in example B, you'll notice the degree of the numerator and the denominator are the same. They're both raised to the second power. And then if you notice the answer, what do you notice about the answer? Well, the answer is simply the coefficients of those terms. So keep that in mind if the degree of the numerator and denominator are the same. Alright, moving on to example C. Again, if you want to try this on your own, feel free to pause the video. Otherwise, I'm going to work this out. I've got the limit as x approaches infinity. Again, our highest power term in the denominator is x squared, so I'm going to divide everything by x squared. So this first term becomes negative 2x. The second term becomes 3 over x squared. In the denominator, we have 3, and then 1 over x squared. Looking at each of our limits, the limit as negative 2x, the limit as x approaches infinity of negative 2x, this is just going to keep getting bigger and bigger and bigger, and this negative means it's going to keep getting bigger in the negative direction, so that's negative infinity. This one's going to be 0. Limit as x approaches infinity of 3 is just going to be 3, and then plus 0. So basically what we have here is infinity over 3, which is going to tell us that the limit is not going to exist. Alright, so 3 different cases in this first example. For the first part, we had a limit of 0. Notice that the degree of the numerator was less than the degree of the denominator. Example B, the degree of the numerator and denominator were the same. And example C, the degree of the numerator was greater than the degree of the denominator. So a little summary here. Given the rational function f of x is equal to n of x over d of x, where basically these are just two polynomial functions, the limit of f of x as x approaches positive or negative infinity is going to be as follows. So if n is less than m, that's like example A, our limit is going to be 0. If n is equal to m, if the degree of the numerator and denominator are the same, then our limit is just going to be the ratio of the coefficients of those largest powered terms. And then if n is greater than m, if the degree of the numerator is greater than the degree of the denominator, then our limit is not going to exist because the limit of our numerator is going to approach infinity. Alright, so here's a couple of examples. If you want to go ahead and pause the video and try these, feel free. I'm going to pause my video and just write in the solutions for these so that you can just check when you restart the video. Otherwise, if you keep the video going, these are just going to pop right on there. So again, pause if you want to, or wait for the answers to pop up. So here's the solutions or the answers for this last try it example. You may want to pause the video as you check these, And again, if you're not sure how to do any of these, or if you want to go through and divide each term by the power in the denominator that's the greatest, you can do that as well and work out the limit the way we did in the first example. Otherwise, again, make sure you ask questions if you have them, and we will see you in the next video.